Okay.
Yeah, now it's working again.
Okay, sorry. Let's see here. Okay, so well, it doesn't matter. No problem. So okay, okay, we were not recording. Well, okay, well, doesn't matter. So well, the thing is that of course this is a very nice result which holds in any quantum field theory. But there are still some problems or some questions that arise. The first is that the Unruh temperature is extremely small to be measured directly, because if you restore the fundamental constants of nature in the Unruh temperature, you get that in order to get a temperature which is of the order of 1 Kelvin, then you need accelerations which are 10 to the 20 times the Earth mean surface gravity. Okay? Moreover, we see here that, of course, this is the typical thermal density matrix that we all know. But, well, we can think, is this a real thermal matrix, or is this just a formal analogy between temperature and acceleration? So the way in which we can shed some light on these issues is just to ask ourselves, well, if acceleration and temperature are going to be equivalent, that would mean that we could just do the same things with acceleration as we do with temperature. And in particular, what we can do with temperature in quantum field theories is to trigger non-dynamical effects, non-trivial effects such as phase transitions. So that's why we ask ourselves, well, can we actually trigger some very fundamental phase transition using the Unruh effect? And in particular, can we apply the Unruh effect to the case of the QCD phase transition, which is both from the phenomenological and theoretical point of view, one of the most important ones in quantum field theory? And that's why we decided to focus on the chiral phase transition of QCD. So, of course, we all know that quantum chromodynamics is the standard theory for strong interactions within the standard model of particle physics. And its Euclidean Lagrangian for two massless flavors is given by this expression here, where we have the gluon fields and the quark fields. Okay, so this Lagrangian is invariant under this group of global transformations, where this SU2 acts only on the left-handed components of the quark fields, and this other SU2 acts only on the right-handed components of the fields. And that's why this group is called the chiral group, and these transformations are called chiral transformations. Of course, notice that this L and this R have nothing to do with the left Rindler wedge and the right Rindler wedge. They refer to the chirality. Okay. So this is a symmetry of the Lagrangian of the theory, but we also know that this theory is not a symmetry of the Minkowski QCD vacuum state. In other words, that this symmetry is spontaneously broken. Why? Because if it were a symmetry of the vacuum, then it would be a symmetry of the whole hadronic spectrum. And when we go to take a walk in the park, we do not see left-handed pions and right-handed pions, for instance. We see pions. So this means that this symmetry must be spontaneously broken. How can we measure how much this symmetry is actually broken? Well, we can construct some operators that explicitly break this chiral symmetry and compute its vacuum expectation value in the Minkowski QCD vacuum state. The simplest such operator is this one, which is called the quark condensate. And as we can see here, it mixes both left-handed and right-handed components of the quark fields. And of course, its expectation value then will be a measure of this breaking of chiral symmetry. If we compute it at zero temperature in flat spacetime, we get some value which is non-zero, which is okay. It means that chiral symmetry is broken. But if we switch a finite temperature in flat spacetime, we see that this quark condensate becomes a function of the temperature. And we see that it starts decreasing from its initial value, and it reaches zero at a certain critical temperature, which is proportional in most models to the pion decay constant. Okay, and from that point on, then it stays 0. And this means that we have actually restored chiral symmetry for temperatures high enough, in particular for temperatures which are higher than the critical temperature of this phase transition. Okay, and we also see that this is a typical second order Landau-Ginzburg phase transition because the order parameter is continuous at the critical temperature, but the derivative of the order parameter is not continuous. Okay, so this is what we can do with QCD at finite temperature in Minkowski spacetime. So what we asked ourselves is, well, can we reproduce this computation using Rindler spacetime and no temperature introduced by hand, but only the Unruh temperature? And that's what we did in our work. So how do we compute this quark condensate in the right Rindler wedge? So we first need to choose an effective description for QCD at low energies, because this will be a low energy phenomenon, okay? And why do we need an effective description of QCD for these low energies? Well, we know that QCD is an asymptotically free theory, okay? And this means that the perturbative degrees of freedom, which are those that appeared in the Euclidean Lagrangian that I showed you before, the quarks and gluons, will be the relevant degrees of freedom only when the coupling is very, very small. And that means that they will be the degrees of freedom at high energies or high temperatures, where we will have a quark-gluon plasma. However, when we lower the energy or we lower the temperature, these quarks and gluons will be forced to form hadrons because the strong interactions becomes stronger and stronger whenever we lower the energy or the temperature. So this means that for low energy phenomena, we need to have an effective description whose effective degrees of freedom are hadrons, and in particular the lightest hadrons, which are the pions. Okay, this effective description of QCD is called chiral perturbation theory, but here we only need to use the first term in such an expansion, which is a nonlinear sigma model, okay, whose partition function is given by this path integral, where we have an effective action with the pion fields, which are now our effective degrees of freedom. We have an extra sigma field, which is related to the pion fields through this constraint, which is in turn imposed into the path integral using this auxiliary lambda field, which is just a Lagrange multiplier. Okay, and we see here that we have introduced the determinant, the square root of the determinant of the Rindler metric, because we are computing this in the right Rindler wedge. Okay, comparing this partition function with the one that we obtained from the full QCD action, we see that the expectation value of the sigma field in the Minkowski QCD vacuum state is proportional to the quark condensate. And therefore, if we want to compute this, which is what we want, we have to compute the expectation value of sigma. Okay, so how do we do that? Well, we have to compute this path integral. And how do we do it? Well, as we see here, the integral over the pion fields is, well, straightforward to compute because it's a typical Gaussian integral. So it's okay. And the two remaining integrals can be computed using a saddle point approximation in the large n limit, where n is the number of pions in theory. In this limit, we choose f pi to be proportional to the square root of the number of pions, and then we expand the fields around the point in functional space where the first derivatives of the effective action vanish. Okay, this is just like taking the most classical solutions. Okay, so if we do so, we find that the value of the sigma field in this point is proportional precisely to the square of the expectation value of sigma, which is in turn proportional to the quark condensate. So this is just what we want to compute. So doing this, implementing this, we find a system of equations, including one for a Euclidean green function. And these equations can be solved in the limit in which lambda is approximately equal to 0, which means that the thermal pion mass is 0, okay, because it's very small. And skipping all the details, because they are irrelevant here, what we find in our article is that if we define the n-independent critical acceleration in this way, okay, we obtain that the quark condensate is given by this expression here. Okay, and we see that this is very, very similar to what we obtained at finite temperature in Minkowski spacetime. But now there is a weird thing that is this dependence on this x coordinate, which I haven't talked about yet. Okay, so what is this x and why is this x here? Well, in order to understand what this means, we have to introduce these two new coordinates, which are comoving coordinates for Rindler observers, small t and small x. This is the same x in the previous expression. And these two coordinates cover only the right Rindler wedge. They are defined in this way. And they have the special property that if you choose any value of x, any constant value of x, then the world lines corresponding to that choice are precisely hyperbolas. They are accelerated trajectories. And if we change x, we are just changing the accelerated trajectory. Okay? This x is defined in such a way that if we take x to be equal to 0, then we have the hyperbola with a constant proper acceleration a. And if we choose any other value of x, then we have that the acceleration of that hyperbolic observer is given by a times the exponential of minus ax. And if you remember, this is precisely what we had here. So if we replace this by the corresponding acceleration, what we see is that this expression now becomes completely analogous to that of QCD at finite temperature in Minkowski spacetime, because this just tells us that we can choose whatever acceleration we want, and of course, when the acceleration reaches the critical value, then the quark condensate will vanish, and we will have restored chiral symmetry for the accelerated observer. Of course, this can be seen pictorically here. We have the critical hyperbola corresponding to the accelerated trajectory with the critical value of the acceleration. And if we have accelerations which are lower than the critical value, then we'll be in the broken phase. But if we have accelerations which are larger than that, we'll be in the restored phase. And of course, this is essentially the same that we got in QCD in finite temperature. But here we have a little plot twist. And it is that, of course, from this expression here, we can infer correctly that Rindler spacetime is no longer homogeneous and isotropic, unlike Minkowski spacetime. And in Minkowski spacetime, we had the same temperature at all points. But here we don't. We have a temperature which depends on the point. And this means that we can play with this a little bit. And notice that if we consider any trajectory, any accelerated trajectory with an acceleration lower than the critical one, then here, very, very close to the horizon, this trajectory looks very much like the critical hyperbola. And in particular, it looks very much like any other hyperbola, close enough to the horizon. So exploiting this inhomogeneity and anisotropy of Rindler spacetime, what we can find is that here, very, very close to the horizon, any accelerated observer will see a restoration of chiral symmetry if that observer looks in the direction of the horizon, because this hyperbola will be very, very close to the critical one, which separates the restored region from the broken region. Okay, so just to sum up what we have here, well, we have just seen that the powerful functional formalism of Lee's thermalization theorem allows us to extend the Unruh effect to any quantum field theory that we like. And this allows us to prove whether this Unruh effect means that the Unruh temperature is completely equivalent to a real temperature, or if it is just an artifact, you know, a formal result, okay? We have tested this by focusing on a particular case of great physical relevance, which is the chiral symmetry of QCD. And we have obtained that in this case, we can restore chiral symmetry just as we do in Minkowski spacetime at finite temperature using acceleration. And in fact, we get for n equal to 3 pions, okay, which is the physical one. We find that the critical acceleration, the critical temperature corresponds to the critical acceleration, because you see that AC over 2 pi is the Unruh temperature corresponding to the critical one. Okay, and in principle, these results could be extended to black holes, the Sitza space, etc. Okay, because they are also spacetimes with horizons. The computations become very involved, though. And thus, at least in principle, this work may have applications both in cosmology, astrophysics, and maybe heavy ion collisions, where the Unruh effect has been proposed like 15 years ago as a possible thermalization mechanism. And that's it. Thank you very much. Moltes gracias y muchas gracias.
Okay, Adrián, thank you for your nice talk. I really like it, so I think everybody also likes it.
Thank you.
So, do you have any question, any comment? Let's wait some minutes to see if somebody wants to ask. If not, can you repeat what is the relation between the capital X and T and the small x and T in relation with the critical acceleration? Can you repeat this, please?
Yeah. These are, okay, so the problem here is that we have used highly non-standard notation, okay? So typically, this X is called Xi, and this T here is called eta. So these are the standard Rindler co-moving coordinates that one introduces when studying the Unruh effect. And the thing is that if you choose a word line which has a constant X, you can check that it corresponds to one and only one accelerated trajectory. Okay, so of course, if you change the value of X, you get different values of the acceleration. And in particular, if you want to get the critical acceleration, you need to choose a particular value of X, which is this value of X. And that's it. It's
okay.
It's no mystery here.
Okay. Thank you. So, do you have it?
I have a question. So,
yes.
So do you mean that if we have two observers, one at rest and the other accelerating, they will observe the system in different states?
Well, the thing, yeah, I mean, yes, but the state of the field is the same because it is the Minkowski vacuum state of the theory. However, the thing is that the accelerated observer will perceive such a state as a thermal bath of particles. And this means that because there is a temperature, then the accelerated observer will be able to see a phase transition that the static or the inertial observer will not be able to, unless that inertial observer introduces a finite temperature by hand.
Okay. So, and in the other Rindler wedge, they will see the same transition, right?
Yeah, that's it. The results are completely analogous because the thing is that movement takes place in just one of the two Rindler wedges. And of course, because you can interchange both of them by a change of sign, basically. The idea is that you can choose one and go. The thing is that here we have chosen, even moreover, we have chosen acceleration to be on the X direction. I don't think that I said that before, but we have chosen acceleration to be in the X direction without loss of generality because we can reorient the coordinates.
Okay, thank you.
Okay, thank you.